Hey Royals! In today's lesson, we're going to talk about relative motion. Now, motion in general requires a frame of reference. And most often in our world, we use the frame of reference known as the Earth. So if I'm traveling in my car and I'm driving down the road and I'm traveling at 60 kilometers an hour, that is relative to the Earth. Now, I have a video here to demonstrate what we mean with different frames of reference. So go ahead and watch this video. And what I want you to see is the gentleman who walks by in the background. He's going to travel a heck of a lot faster than the woman in the foreground. And then I want you to discuss with yourself what is actually happening in this video. Welcome back. So in the video, you may have noticed that this woman was walking on a conveyor belt and she wasn't making much progress. But if you imagined that she had blinders on, she couldn't see around her, she would think that she's moving at, say, 5 kilometers an hour. But to the general public watching her, she was actually probably moving at about 1 kilometer an hour. And then she stopped and she actually started moving backwards. Right? So this is all relative to different viewers. So the person on the conveyor belt saw their motion moving a whole lot faster than the people watching it from the sidelines. So what we need to understand with this is that motion is relative to the frame of reference. So imagine you're in a situation where you're in a canoe and you're able to paddle at 4 meters a second in still water. Now, I'm going to introduce a current in that water, and it's going to travel at 1 meter a second south. Now, assume that I'm traveling in the same direction that the current's flowing in. It doesn't take very difficult math to understand that if I'm able to paddle at 4 meters a second, and the water's moving at 1 meter a second, then somebody watching me from the sidelines is going to see that I'm moving at 5 meters a second. And that's because I have 4 meters of my paddling power, plus the 1 meter a second of the water push me along. So what we want to do there is we want to define velocities relative to different objects. So when we do these types of problems, we're going to have an object, then we're going to talk about what unit we're talking about. So we're talking about velocity here, and then we're going to have the other term here as the frame. Okay, so all of these subscripts mean something to us. So in the case of this equation here, the R is going to represent the rower, the W will represent the water, and the G will represent the ground. Okay, so that means that the rower's velocity relative to the ground, so somebody watching the rower from the shore is going to see the rower relative to the water, that's 4 meters a second, and then added to it will be the vector of the water relative to the ground. So they have to add these two motions together to explain what they're seeing. Now imagine I turn around and I'm rowing back the other way. So I'm traveling 4 kilometers an hour north, and the water's traveling at 1 kilometer an hour south. Now, to somebody watching me, I will only be moving at 3 kilometers an hour relative to the shore. Or actually, in my picture, I have it as kilometers. In the equations, I have it as meters per second. So let's leave it as meters per second for our understanding of the equations. So 4 meters a second north plus 1 meter a second south. If I'm going to add vectors, I want to remember that I need them to be added in the same direction. So I need both directions to be north. So I'm going to change the direction of my south to north by just simply introducing that negative sign in front of my magnitude. So in fact, I have 4 meters a second added with negative 1 meter a second to result in 3 meters a second north. Okay, now air pilots need to consider this because they have something called ground speed, and that's actually supposed to be ground velocity, and it's going to be how fast they're moving relative to the Earth. So if I'm flying from Toronto to Vancouver, I have to account for the fact that the wind might be acting as a headwind, meaning straight at my face. So the velocities that they will take into consideration when they're talking about ground speed or ground velocity will actually be the plane relative to the air, how fast the plane can push through this liquid known as air, or this fluid known as air, and then how fast the air is moving relative to the ground. We call that wind, right? So this should actually say plane relative to the ground, not plane relative to the water, but it is another fluid. The ground and air is my fluid that I'm traveling through. Okay, so we're going to do some problems that revolve around this relative motion and similar to our canoeist in the water. And then in our next lesson, we're going to increase it to deal with velocities that might be at 90 degrees to each other, or so two-dimensional relative motion.